Okay, so we now start chapter 4 on Newton's laws of motion. And Newton's laws of motion really were sort of, Newtonian theory was sort of the first time that we as humans kind of did science in a very systematic way. And Newton's laws of motion that we will study in this chapter, it really sort of, so far we've been talking about like things that are moving at constant acceleration, and we got these relationships between position, velocity, time, and so forth. In some sense, in a way, there was no physics in it, in the sense that we gave a definition of what is displacement, we gave a mathematical definition of what we mean by velocity and by acceleration, and mathematically, there were just relationships between them, and we just tabulated those relationships. In this chapter, we will address the question of what causes something to accelerate in the first place. And we will see in this chapter that whenever something experiences a net force, it begins to accelerate. And that is one of the laws of Newtonian theory. So Newton's laws of motion describe the relationship between the motion of objects in our everyday world and the forces acting on them. So in some sense, we have not explicitly talked about forces up until now. We kind of alluded to it, that when you throw a ball up in the air, it falls back down because, quote unquote, there's a force of gravity. But really, the only information that we used from it is that observationally, there was an acceleration due to gravity, which was 9.8 meters per second squared pointing down. Well, we didn't really talk about why it is accelerating down with 9.8. And so that's the kind of stuff that we will address next. So, the motion of planets, stars, the moon, falling objects, projectiles, satellites, cars, planes, rockets, all of this, we put man on the moon using Newtonian physics. And as I mentioned in the very first lecture of this class, we should keep in mind that Newton's laws do break down when you start looking at physics at the subatomic level, or when objects are moving near the speed of light, or if you're next to a black hole or something, then you need to extend your theories. So we will focus, for most everyday phenomena we experience, Newton's laws of motion are an incredibly good approximation for describing the world, good enough to put man on the moon and put satellites into orbit, and then we're all on Facebook or whatever. So it's good enough for all of that. This is kind of what I mentioned earlier. And this is really a very remarkable story. It had, very deep implications. Sometimes we're all like, we're doing physics and we're doing math and we're doing our equations. But really, when this all started, it really had profound implications for understanding our place in the universe. So as you all know, back in the day, people thought that the Earth was at the center of the solar system. The sun, all the other planets, everything was moving around the Earth. A pretty reasonable assumption, because we seem to be kind of stable here, and everything around us seems to be moving. But of course, we figured out eventually that we're the weird ones. We're the ones that are spinning. And that's why, from our point of view, the rest of the world appears to be spinning. And so for over 1,500 years, people tried to understand the laws of motion that govern the motion of planets and stars in the sky. And even though they had the physics wrong, the physics understanding of it, what they did was really remarkable. So what you're seeing here in this complicated picture, this is the geocentric model of the universe that they had, that we were at the center. And this is what we observed from our point of view. Everything was moving around us. And if you look at the motion of planets like Mars or something like that, and you keep track of its position in the sky over the year, what you find is that it seems to kind of take these sort of elliptical paths. These are in the sky. You may have heard about like Mars retrograde and all that kind of stuff. So usually Mars is going across the sky this way, and then all of a sudden, for a brief period, it turns around and goes the other way, and then it turns around back and goes forward. A very, very complicated motion in the sky. But the astronomers at the time, they were very, very good at taking this data, and so they mapped out very precisely all of these trajectories, and it looked like a real mess. And then, of course, Newton and Copernicus and all these people came along, and they realized that actually you can explain all these weird motions, all these weird paths, if you're just willing to give up that we are not at the center. The sun is at the center, the heliocentric model, and we're one of many planets going around. And so essentially what happens is, for most of the, from our point of view on Earth, Mars is kind of going this way, but every now and then, as we're both orbiting the sun, we might like overtake Mars from the inside, like a race car. And then all of a sudden, from our point of view, Mars appears to go backwards in the sky. And that's literally what is happening over here. But it required for us to give up the idea that we were at the center of the universe, essentially, for them. And that was emotionally a hard thing for many people to do. This is Isaac Newton. He's probably one of the best physicists of all time. He formulated the basic concepts and laws of mechanics. He developed the universal theory of gravitation. He developed lots of physics in light and optics. He was able to understand, the colors of a rainbow, stuff like that. And while he was doing all this stuff, he was trying to explain planetary motion. He realized that in his time, he did not have the mathematics needed to describe it. So he takes a little detour and he kind of invents calculus along the way. And he did all this like by the time he was like 26 or 28 or something like that. So just kind of a crazy guy. In our defense, he was in a cottage somewhere in England with no internet. You can be a lot more productive probably that way. In fact, let me see if I can find a YouTube video on, you guys know Neil deGrasse Tyson? He has a little take on Newton, which I think is kind of funny. Okay, so here it is. So this is Neil deGrasse Tyson talking about how great Newton is.
Let's go help people customize and save with Liberty Mutual. Okay, who sat at my desk?
Isaac Newton, I mean, just you read his writings. Hair stands up on, I don't have hair there, but if I did, it would stand up on the back of my neck. You read his writings, the man was connected to the universe in ways that I've never seen another human being connected. It's kind of spooky, actually. He discovers the laws of optics, figures out that white light is composed of colors. That's kind of freaky right there. If you take your colors of the rainbow, put them back together, you get white light again. That freaked out the artists of the day. How does that work? Red, orange, yellow, green, blue, violet gives you white. The laws of optics, he discovers the laws of motion and the universal law of gravitation. Then a friend of his says, well, why do these orbits of the planets, why are they in the shape of an ellipse, sort of flattened circle? Why aren't they some other shape? And he said, I don't know. I'll get back to you. So it goes home, comes back a couple months later. Here's why. They're actually conic sections of a cone that you cut. And they said, well, how did you find this out? How did you determine this? Well, I had to invent integral and differential calculus to determine this. Then he turned 26. Then he turned 26. We've got people slogging through calculus in college just to learn what it is that Isaac Newton invented on a dare, practically. So that's my man, Isaac Newton.
All right. Okay. Any questions about that? So let's talk a little bit about forces. So we haven't talked about it in detail as much. And we have some intuition for it from our daily lives. A force is usually imagined as a push or a pull on some object. So this person kicking on the football is pushing on it, that exerts a force. This person is pulling on this handle, they're exerting a pulling force, and so forth. So these forces can typically be classified into two types. They're called contact forces, where there's physical contact between things when the force is being exerted, the push or the pull. There's also other types of forces called field forces, where it appears that objects can exert a force on each other even without touching them. So for example, when you take two magnets together, you know that they exert a repulsive or attractive force, and depending on how you hold them. And they do it even though there's no physical contact between them. They kind of reach out to empty space and exert a force. Gravity is another example of that, right? The sun reaches out through 93 million miles of empty space and tugs on the earth. And then there's also electrical forces between charges, say between the nucleus and the electron and atoms. Again, there is no physical contact between them. In some sense, this distinction between contact and field forces is a bit artificial because, at a microscopic level, even these contact forces really are field forces. Because if you go down really to the microscopic level, there's essentially a repulsive force between the electrons in the atoms of the foot and the electrons in the atoms of the football. They come real close together. They exert a sort of an electrostatic repulsion. But from our sort of macroscopic point of view, that looks like a contact force. So in physics 2, if you take physics 2, you will learn more about electrostatic forces at this microscopic level. But for the purposes of physics 1, we will be looking at macroscopic phenomenon, and from there, it is most useful to kind of classify things into contact and field forces. Any questions on that? And in fact, this is not, you shouldn't even think of this as necessarily just like an approximation or something. And from the point of view of physics, in a way, it's really the right way to think about this classification. It's an important part of physics, which is that you don't have to know everything in order to explain something, right? So we don't need to know that things are made up of atoms and that there's electrical forces between them and all this kind of stuff. Newton, did not know about any of that stuff, but he was able to do a lot of physics because he was like, well, let's just treat this as a contact force. And in some sense, if you try to keep track of every electron in the foot and every electron in the football trying to explain this problem, then you're not approaching the problem in a smart way, right? You're just complicating it way too much for the purposes of what you need. It's sort of like you don't need to know nuclear physics to build a boat, even though you know that the sail and the wooden part of the boat is ultimately made up of atoms and nuclei. It's just overkill. So we kind of classify things as needed. And speaking of forces, again, at a fundamental level, there are 4 types of fundamental forces in nature. All phenomena that we observe can be boiled down to a consequence of these 4 forces that are governing the evolution of our universe in every sense. There's gravity, there's electromagnetism, and then these are the 2 forces that we're most familiar with. We're stuck to the earth because of gravity. We all have experienced at some point electrical shocks and magnets and things like that. And then there's 2 more mysterious forces. There's something called the weak nuclear force and the strong nuclear force. And obviously the reason we're less familiar with it is because the range of these forces is very small. It's confined to within nuclei, and we're all much bigger than nuclei, so we don't have a sense for these two types of forces all that much. Whereas gravity and electromagnetism are long-range forces. We can feel them over long distances, like magnets and planets and so forth. Any questions on that? Forces are vectors. They have magnitude and direction. So you can have situations where there are multiple forces acting on something, and you want to find what is the total force on it. It really boils down to a problem of vector addition. So all this technology of vectors, decomposing them into their components, all that kind of stuff will come back again. So in some sense, we can recycle a lot of the technology. Forces can be added using vector addition, and then we can define the total or the net force on an object as the vector sum of all the forces acting on the object. Any questions on that? All right, so here is Newton's first law. And again, it is a law, meaning that there is no proof for it. It is simply declared as a postulate of the theory. You go test it as much as you can. And then if it checks out, then it gets elevated, the hypothesis gets elevated to a law, and then you work out its consequences. So the first law says that an object moves with a velocity that is constant in magnitude and direction unless a non-zero net force acts on it. So in other words, if the net force on an object, you add up all the forces acting on it, if that net force is zero, then that object will have constant velocity. It might just be sitting there, which in which case it has zero velocity, which is constant. Again, it's constant zero velocity. Or it will move with a constant velocity in a straight line forever and ever. Okay. So for example, there's things, there's things sitting on the table. There's a force of gravity down. The surface of the table is pushing back up. That net force is zero. And so therefore, it just sits there with zero velocity forever and ever. How many of you think that this law is obvious? Is it intuitive to you guys? Does that make sense? It's intuitive to us today, I think. But back in the day, it was actually very, very non-intuitive. And in fact, for the 1500 years before this, there was a quote unquote first law that was exactly the opposite. It was by Aristotle, and he had declared that the natural state of an object is to want to be at rest. And he was basing that on the idea that, well, when we look at things all around us, if you get a ball rolling, you know that eventually it comes to a stop. And so therefore, he concluded that the natural state of things is to be at rest. And it really took 1,500 years for people to even get this first law right. And you can see a problem with it because if you have an object that's sitting at rest, from your point of view, it's at rest, but if someone's going by in a train, from their point of view, it's moving with constant velocity, right? So in some sense, there is no sense of absolute rest in Newtonian physics. It depends on what frame of reference you're looking at. So here is the, if you take a book and you slide it across a rough table, we all know that eventually it'll come to a stop. And that's because there is a net force acting on this book. There's a force of gravity down, the table is pushing back up on it. Those two forces basically cancel out. So there's no net force in this direction. But then because the surface is rough, there's a force of friction. And we'll talk about what the force of friction is a little bit more in detail. But essentially there's interactions, at a molecular level between the molecules of the book and the table, and that force manifests itself as a force of friction at a macroscopic level. And so as this is going along, there is a net force to the left that causes it to slow down, that causes it to accelerate, and therefore causes it to change its velocity. It had some initial velocity here, and then it comes to a velocity where it is now 0. On the other hand, we know, and this is how Galileo, I think Galileo was responsible really for this first law. He took Aristotle's hypothesis that everything likes to be at rest, and he realized, here's how you can understand that that's not quite right, is because if you take this table and you make it smoother, then what's going to happen is that this book is going to slide a longer distance before it comes to a stop. And then you make it even more smooth, it's going to slide even longer distance before coming to a stop. If you put it like on an ice rink, it's going to slide a very long distance before coming to a stop. And so he imagined if you could make this surface infinitely smooth, it would just keep going forever and ever. That's when the force of friction is exactly 0. So if you put on a frictionless surface, it will keep going. So if you take a ball and you go into outer space and you chuck it in some direction away from any planets and stars or whatever, it will keep going in a straight line with that velocity forever and ever until the end of time. It's kind of remarkable, actually. All right. I think this is a good place for me to stop. So let me go ahead and stop here. And I will see you guys on Friday, test 1. Let me go ahead and stop the